Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference. Mathematical Revolutions, From Arithmetic to Parallel Thinking. A brief history of mathematics, focusing on the evolution of optimization applied to real-world problems. It corresponds to one of several short conferences, in which the advances of high research are presented, on the topic of artificial brains and decision-making artificial intelligence. The list of short introductory lectures to decision-making artificial intelligence are presented in the picture. The origin of mathematics is the arithmetic, which begins its development with the appearance of humanity. Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world. The appearance of algebra is in the near to the year 800 BC. Many centuries passed since the apparition of arithmetic. Muhammad ibn Musa al-Khwarizmi, mathematician and Arab astronomer, introduced European mathematicians into the Indo-Arabic numerals and in the fundamental principles of algebra. The evolution of algebra starts from a school notation, oriented to small models, not scalable, to become a professional, industrial, and scalable algebra, oriented to the present modeling of the large systems that make up the real world. If two algebraic formulas are joined, a new algebraic equation is obtained that retains the same structural characteristics of the original equations. This transitivity law may be extended to mathematical programming models, MP, which in essence is a collection of algebraic elements. Additionally, the entire mathematical representation of a controlled real-life system is represented by one and only one reduced-form math model, using algebraic equations to describe the system and its dynamic. It can be said that there is only a reduced way to write an algebraic equation. This is independent of the symbols that are used to represent the physical or logical relations. Then it is possible to join two MP problems to obtain a new MP problem. It is also possible to divide an MP problem into two MP problems. The principles of transitivity between MP models can be extended to more complex structures, such as those derived from the partitioning and decomposition of systems, to apply large-scale optimization methodologies. In this way, the new vision of mathematical programming involves defining the relationships between problems, as the next step after the definition of the equations that compose them. The difference that mastery of algebra creates with respect to arithmetic is an abyss, is not a gap. Perhaps the second great mathematical revolution, it is the birth of the fundamental principles of optimization, based on differential calculus. René Descartes was a French mathematician, physicist and philosopher, considered the father of the algebraic and differential geometry. Sir Isaac Newton was an English mathematician, physicist, astronomer, and theologian, widely recognized as one of the greatest and most influential scientists of all time. He was a key figure in the philosophical revolution known as the Enlightenment. Newton made seminal contributions to optics, and shares credit with German mathematician Gottfried Wilhelm Leibniz for developing infinitesimal calculus. Joseph Louis Lagrange was an Italian mathematician and astronomer, later naturalized French. In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. Using the implicit function theorem, the seminal Lagrange idea is to convert a constrained problem into a form such that the theory of an unconstrained problem can still be applied. The creation of the digital computer gives rise to modern mathematics, oriented to the production of algorithms that can solve complex problems in a computer. George Bernard Dantzig was an American mathematical scientist who made contributions to industrial engineering, operations research, computer science, economics, and statistics. Dantzig is known for his development of the simplex algorithm for solving linear programming problems, and for his other work with linear programming. In statistics, Dantzig solved two open problems in statistical theory. The primal simplex algorithm can be considered the starting point of applied mathematical programming, and the birth of computer-oriented mathematics. Mathematical programming is characterized by having an objective function as decision criteria, and a mathematical model, based on a set of constraints that represent the industrial's process, and The business rules. Since its birth, computer-oriented mathematics has evolved in speed, and in the ability to solve increasingly complex problems. The image presents the evolution of the Gurobi solver, from its first version, in 2009, to the last in 2023, this for discrete optimization problems. The difference that the mastery of computer algorithms creates with respect to the solution of problems by humans, is an abyss, is not a gap. In a relatively short time, 25 years, mathematics oriented to parallel computing emerges. This new revolution is not pressured by parallel processing, since it did not exist. The pressure is generated by the need to speed up the solution of large problems in a digital computer. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. Benders partition, or Benders decomposition, is a technique in mathematical programming that allows the solution of very large mixed linear programming problems that have a special block structure. This block structure often occurs in all real applications. The importance of Benders' theory, which followed the work of Danzig-Wolff, is that it resulted in parallel optimization, based on the theory of duality. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex, which today is the key to a dynamic language for cognitive robots, based mathematical programming algorithms to build artificial hypothalamuses. Duality theory is the key to create a generalized language between robots, or algorithms, that represent different types of systems. Today, it is the support of parallel and distributed artificial intelligence, that is the base of artificial brains. The growth of parallel optimization-oriented technologies has been significant over the past 2 decades. The image presents the growth of Benders' theory from its inception in 1962 to 2016. The green bars, based on a visual projection, presents the expected growth in these years, which is exponential. On the other hand, the speed increase provided by large-scale theories is significant. The table provides information on various types of problems, solved with several variations of Benders' theory. The column time ratio solver/Benders presents the relationship of solution times for different sizes of problems. The content is Benders times faster. In 1983, Tony Van Roy created the cross-decomposition approach to solving large-scale optimization problems, based on partitioning and decomposition techniques, and mixing different types of methodologies, such as Lagrangian relaxation and Benders' theory. Given the complexity of the real world, which involves mathematical models of all types, linear, nonlinear, discrete, continuous, convex, non-convex, etc., it cannot be thought that with a single methodology, all the problems that make up an artificial brain can be solved. Therefore, it is required to have access to multiple large-scale optimization methodologies, which, using the principles of cross-decomposition, connect all mathematical problems, to perform autonomous distributed optimization in real time. Cross-decomposition makes it possible to establish complex optimization processes, in which multiple large-scale methodologies are used, which allows to adjust the problems to the most convenient methodology for the solution of each subproblem. From the point of view of multi-layer structures, cross-decomposition gives rise to the exchange of information between multiple layers, of different columns, such as the real structure of the human neocortex. In 2004, General Algebraic Modeling Systems Incorporated, GAMS, reported experiments in the speed gained using 200 CPUs in parallel was 60 to 1 times faster, with its corresponding benefit in accuracy, if parallel processing is used to increase the quality of the results. The union of large-scale technologies with parallel computing is increasing every day. The image indicates that a complex optimization problem, which can be solved in a unit of time, say an hour, using simple sequential methodologies, could take 400 hours, 16.66 days. If the appropriate technologies are not available, an unsuspecting professional would conclude that the problem cannot be solved in a reasonable time. Again, The difference that the domain of large-scale optimization creates with respect to sequential optimization is a chasm, not a gap. Computer power and mathematical programming. All the developments in mathematics applied to solving real-life problems converge to parallel processing and the large-scale mathematical programming. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, which are the beginning of a new era. The current state of the computer technologies involves the integration of edge computing and cloud computing to implement systems with multiple highly complex mathematical models that can be run in parallel. This allows us to talk about autonomous real-time distributed optimization. The image presents an exponential forecast for the growth of quantum processing power. The difference between supercomputing and computing creates a chasm, not a gap. Algorithms swarm, the actual state of artificial intelligence using artificial brains. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. Two different worlds. Without fear of being wrong, it can be said that as people and organizations travel the path from arithmetic to parallel thinking, an abyss is being generated, which is concretized in the speed with which a society produces knowledge and wealth. The new way of mathematics is directly related to the parallel thinking, and today it can be said that, like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Not teaching young professionals the principles of parallel rationing, derived from the new mathematics, is a serious mistake. Each society that does so will end up paying its consequences, which in simple words, will lead to poverty and a growing scientific backwardness, an abyss, which generates two different worlds that will not be compatible. Finally, there are now in the world machines that think, that learn, and that create. Moreover, their ability to do these things is going to increase rapidly until, in the visible future, the range of problems they can handle will be coextensive with the range to which the human mind has been applied. In 1972. In the book Human Problem Solving, wrote by Alan Newell and Herbert Simon. Thank you very much for your attention.